So 6.2 radian measure. This part here that I'm going to go over is a review of grade 11. So like I said, I'm going to go through a little bit quicker because I'm not trying to teach it. I'm just trying to refresh your memory as to what we already know. So we know that whenever we were drawing angles on the quadrants, we were looking at in terms of related acute angles. So I'm going to draw this here. I'm going to try to do this neatly. Okay, you don't have to be this neat. I'm going to try to draw it neater. So we have an angle here. We would always drop it down towards the x-axis at 90 degrees, right? So whenever we drew these, we were drawing it down towards the x-axis, and the 90 degrees was on the x-axis. So we had all of our same triangles. These are supposed to be the same. Sorry, they're a little bit different, but basically we're doing the same thing throughout. Whoops. This one missed. Okay, 90 degrees this way, and that sort of thing. So whichever, sorry, my circle's a little off, but close enough, you get the idea. So there you go. So it's always dropped straight down towards the x-axis. The 90 degrees was here. The angle of reference that we used when we did SOHCAHTOA, right? So when we do SOHCAHTOA for any of these triangles on this unit circle here, the angle of reference was always this one. And what do I mean by your angle of reference? This is the one that's telling you the opposite, the adjacent, and the hypotenuse. So that's your angle of reference. So it's always the angle that's in between the terminal arm and the x-axis, never anything else. We used to teach it two different ways. We only teach it one way now, right? It was worse before because then you get super confused. So we always, the rule is always drop the angle, this here, and this angle here, we used to call it the related acute angle. So I used to use that short form, and it's called related acute angle, right? And we get the RAA from RAA. Okay, and again, this is the way I refer to it, so I don't know if your teacher referred to it, but I would always call it related acute angle. In the homework, they would say, what is the related acute angle? Okay, I would refer to it as little beta b, and I would usually use beta to refer to it in questions and say, what's the beta, right? So related acute angle, beta b. So that's the angle that's our reference. So when I mean by reference, then that's opposite, that's adjacent, that's hypotenuse. So for this one as well, it's between the terminal arm and the x-axis, between the terminal arm and the x-axis, between the terminal arm and the x-axis. So it's never towards the y-axis. My reference angle is always here. All right, so then what else did we have from grade 11? So we knew this related acute angle. Oh, okay, how did we use this related acute angle? A couple different things. So I'm going to add a few more things to this. Again, we're just going through and reviewing all the grade 11, right? So we know that this was CAST, right? The CAST rule. So we know that, right? I'll circle that, CAST. We also, from grade 11, we referred to this as quadrant 1, quadrant 2, quadrant 3, and quadrant 4, right? So sometimes we refer to it in terms of numbers. What else did we do? We did this one. So we said, so if this is my related acute angle, my terminal arm would just be, this one's easy, so we just said my terminal arm went like this, positive in this direction. So that was my positive, and so this is the positive direction, and then when we turned this way, it was the negative direction, right? So that was the negative direction when we headed under. Right, so when we turn this way, it's negative, and that way it's positive. Then, if I said I was going to get to this terminal arm, that meant I was going from the positive x-axis, and I would go around like this, positive direction there. And we counted the angle from the terminal arm here, the x-axis to the terminal arm here. How did I calculate that big angle here? I would say that this was, to get this angle, I used to say it was 180 minus my little beta b, that little related acute angle. But now we are so much more cool. We are going to now refer to this as pi minus beta. Ooh, we are now in radians. right? So we're going to add this to our knowledge. Okay, not 180 minus beta. It can also be pi minus beta. Okay, so same idea for the next one. So if I was going to say, well, I was going to spin around from my x-axis around to this one. Okay, my terminal arm would be here. And instead of saying it would be 180 plus beta, we would calculate that way. Now we're so much cooler, we're going to say pi plus beta, because now we have stuff in radians. Is that all right? Okay. Then we're going to go all the way around from here, go all the way around to this way, whoosh, to that one, right? And then that would be, we used to say it was 360 minus beta, but now in radians, what would we do? 360 is 2 pi, so 2 pi minus the beta, right? So we're adding just this little bit to our knowledge. I think that's about all we remember from there. Again, we're trying to review how we use this. Conclusion. Oh, so also, sorry. This we know is, if this is my coordinate there, we would say if this was x, y, then we know that this line here is x. Is that okay? So this base here. And then upwards, it's y. So I would grab that, and I would say, so for the triangles, we know that this is x, and this is y. And I usually referred to this one here as r. The hypotenuse is r because it's from the unit circle. So if you grab it over here, we grab it over here, like that, from here to here. Does that make sense? Right, so x was the base, y is up, right, and r was this way. So that was my kind of general formula for any of the triangles, x, y, and r. And then from here, we could say that then that means that sine, when we have it in coordinate system, right, as a coordinate, we can think of it in terms of y. So, so much knowledge. So ka toa. So that's y over r. Cos is ka, so it's x over r. And tan is toa, opposite over adjacent, so it'll be y over x. All right. Get all that back into your head. So we've got that back into your head. Castro, related acute angle, how to get the terminal arm, all that stuff, and then this nice little ratio. Now, special triangles, let's do those. It's a lot of little reviews. So special triangles, we have, again, you don't have to do this neatly. I'm going to just do my hand-drawn triangles. I'm going to do one. I'm going to do a 45. I'm going to draw it twice because I'm going to do one in radians and one in degrees. Okay, so I'm just going to draw it twice so I don't have to overlap in my diagram. And then I'm going to draw this one as well. So this one is I'm drawing it twice, like that. So this one here with the two sides being the same, that was my 45, 45 triangle. I don't have to write it on both. We know they're the same. This triangle here was my 30, 60 triangle, right? We took the equilateral triangle and cut it in half. Again, I'm not going to go back to the basics of it, but that's 30, 60. So these special angles are ones that we asked you to memorize, because whenever I asked you sine of 30, 45, or 60, I never wanted you to go to decimals anymore. These were the ratios that we wanted to do exactly. Okay, so 30, 45, 60s were special. Also 90, 180, 360, those ones as well. We'll get to those in an example in a minute. So now what we're doing is we're now going to be writing, and the ratio was 1, 1, root 2. 1 squared plus 1 squared is that, right? Here, make sure you memorize this one right. As soon as you memorize it wrong, every time you use this ratio, you will be losing the marks. every time, right? So you don't want to memorize this one wrong. The way we had it was, remember we had, okay, I'll just refresh your memory down here. It was the equilateral triangle, right, like that, but we cut it in half. So that's where we got the 30 and the 60 from. So that's where we got our knowledge from. It was the equilateral triangle, right, where they were all equal, the same, and then we cut them in half. So we did that, and we said, well, we're going to call this one 2, 2, 2 triangle, so I can go a 2 to 1, because I cut that bottom one in half, right? It was a 2, 2, 2 triangle, and then we cut this so it was going to be 1, 1. So that's where we got it from. Again, you don't have to know this. This is from last year, right? So that's where we got the special angle from, and this one here. So we know that the hypotenuse has to be the longest side. Always opposite the angle, it relates to the side length. So this is 90, which has 2, the longest side. 60 should have the medium side because it's between the 30, which is the smallest angle. So smallest angle across the smallest side, and smallest side across the largest angle across the largest side. It matches, right? So 90 is the biggest, 30 is the smallest. This was root 3. If you ever forget how we use Pythagorean theorem, 2 squared minus 1 squared is root 3. Okay, again, not going over all the basics of it, but hopefully that rings a bell. All right? So now we're going to convert this and do the same thing, but we're going to do this with radians. The ratios will stay the same. So this is still 1, 1, root 2, and this is still root 3, 1, 2, right? So the side lengths will be the same, and the only thing that's changing is that instead of putting 45, remembering our circle, right? So again, try to picture it. We know that this is pi. This is pi over 2, right? Cutting it in half, so pi. This is pi over 2 because you're cutting it in half. If we want half of that, it's pi over 4. And you're thinking that I cut this into quarter slices, 1, 2, 3, 4. So that's why it's pi over 4. So this here is pi over 4. Pi over 4 is 45. The other way you can think of it is 180 divided by 4 is 45. So I go back and forth between picturing it like slices and picturing it like 180. Right? And that's useful. Sometimes you're like, oh, that's easier to picture right now. This is easier to picture. Right? So you kind of want to go back and forth, slices and the 180. So then they're both pi over 4. We're good there. For here, again, if it's 30, remember this is pi. We're cutting it into 30. That means if this is 90, right, so that's pi over 2, that's 90. We're cutting 90 into 3 more slices, 30, 30, 30. So you're converting to degrees and back and forth. 30, 30, 30. So that means I'm cutting this half circle into 6s. 1, 2, 3, 4, 5, 6. So that's why one slice is pi over 6. Also, it's 180 divided by 6. 180 divided by 6 is 30. Right? So back and forth. Either way, they're both good ways to think of it. You kind of want to be able to be flexible and think of it both ways. Slices, and it's also 180 divided by 6. So this will be pi over 6. So 30 is pi over 6. Okay? And then what about 60? Okay, so for 60, we know that that is here, if that's 180, and we know it's 60, we're actually doing 180, so pi, and you're cutting it into 3s. Right? 60, 60, 60, that gets me 180, so that would be pi over 3. So it's the full pi cut into 3, so we know this is pi. Also, it's 180 divided by 3. That make sense? So you kind of want to go back and forth between, I know it's 180 and I know it's slices. So this would be pi over 3. Try not to do slashes, please. I mean, actually just don't do slashes. It just doesn't make sense, because then you're multiplying this by 5, and you're like times 5. You mean the denominator is times 5? No one at this stage should be doing slashes like that. Just write pi over 3, and that way if I have to multiply by 5, it's there. Right? This makes no sense, because you're multiplying the denominator by 5, so no slashes. Okay, so when you're doing fractions, we always want it in fraction form without the slash. Slash is not as useful anymore. Okay, so don't write slashes. So not slashes, so not pi over 6 like that. Does that make sense? It just doesn't make sense because it looks too horizontal with what you're multiplying by. Okay, so put over. Good. Special triangles, we got it now memorized in both forms. All right. Cast rule, we already know. There was nothing really for me to add there. I should just take this off. It's CAST, and it's where the ratio is positive and the reciprocal ratio as well. Reciprocal ratio positive 2. That means positive, sorry. Plus VE, okay? So that's where the ratio, my ratio is positive and the reciprocal ratios. We'll talk about the reciprocal ratios on the next page. So if you're like, oh shoot, what were those again? Yes, cosecant, secant, and cotangent. I have them listed on the next page. So cast rules where the cosine and its reciprocal, right, all of them are positive. Sine, tan, all. Okay, so reciprocal, you're like, whoop, need to be reminded of that. Flip over, next page. Okay.